So I want to work through a couple of theorems with you. I think I've mentioned this in the past, but a theorem is just a mathematical fact. So it turns out that if you know that two functions have this relationship where f of x is always less than or equal to g of x anywhere near x equals a, and you know that both of these limits exist, then you can conclude that the limit as x goes to a of f of x is always less than or equal to the limit as x goes to a of g of x. And so the point is limits respect inequalities. If you have an original inequality and both limits exist, then those limits are going to respect that same inequality. So that's an important thing to just file away in your toolbox. We may need that sometimes, we will. I want to look at a different version, a similar version of the same thing. This is called the squeeze theorem. And so it's a special case here in some sense. Here I want to look at three functions, and I want to assume that this function f is the middle function. So it's bigger than or equal to h of x, and f is less than or equal to g of x for all x near a. Now let's assume that both of these functions actually have the same limit. Well, if you think about it, since I know that f is between these two functions and this function is going to the same thing that this function is going to, then somehow that forces f to have the same behavior. So it turns out that when you know that this function and this function have the same limit, then you know that the limit as x goes to a of f actually exists. And in particular, here's the cool part, then you can conclude that the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, which we already knew was the same thing as the limit as x goes to a of g of x. So all three have the same limit. And this is called the squeeze theorem. And the idea is that the inequalities sort of squeeze the function. Let me graph it for you. So maybe we'll do h, and here's, let's say here's a g, and here's our f stuck in the middle. And so you can sort of see that if g and h have the same limit, let's make this g and this h, and here's f. So g and h have the same limit at this a. This is my point A right here. I should write that down. Then you can see that f is squeezed into the same situation because of the original inequality. So that's called the squeeze theorem. It pops up all throughout mathematics. I wanted to do an example with you, and then I want to show you how we can use the squeeze theorem to evaluate two very important limits that you'll see multiple times throughout the course. So let's do one straightforward example together. I'm going to slide this up. Hopefully I don't make you too dizzy or seasick here. So I want to study this limit with you. This one looks a little daunting to compute directly. It seems like it should be all innocent and happy because it's just a trig function and a polynomial function and a rational function, but the rational function is undefined at 0, so we can't use the direct substitution property. And the sign, the trig function, sort of prevents us from being able to simplify. And so things feel rather hopeless, except for the fact that we should think about what we know about sine of x. We know that sine of anything, let's just say sine of, I'm going to say 1 over x, but I want you to realize sine of anything is always less than or equal to what? To 1, and it's always greater than or equal to negative 1. And again, you could just put a big blank box there. Sine of anything is always satisfies this inequality, and in particular, sine of 1 over x satisfies that inequality. Well, that's not the function that I want, but it's awful close. And as long as I multiply by positive things, then I can multiply this inequality and get the function that I want. So I need an x squared. So I'm just going to multiply this inequality by x squared and conclude that minus x squared is less than or equal to x squared of sine of 1 over x, which is less than or equal to x squared. And now here comes the cool part. You know what the limit as x goes to 0 of minus x squared is. What is it? it's just 0. And by the way, that's the same thing, of course, as x goes to 0 of just x squared. They're both just 0. And once you realize that, this fact, coupled with this inequality, coupled with the squeeze theorem, tells you that we're done. That the limit, I guess I'm going to write in pink now, the limit is x goes to 0 of x squared sine of 1 over x is just 0 by the squeeze theorem. All right, so in the next example, in the next video, I want to work through a couple of examples with you. And one of them is kind of fun. We're going to do a proof by picture. So a couple of more video parts. This is a little bit of a longer section, but it's very foundational. So I wanted to take the time and do lots of examples with you. So bear with me. You guys are doing great, and we'll wrap this up soon.